In this lesson, we're going to look at permutations when there are objects that are identical. Okay, and we'll use this first example to show you what we mean by that. So if you were to take the letters in the word monkey and rearrange them, we already know this question. This is 6 factorial, or you could say 6 permute 6, or you could put the 6 lines like that. Either way, I think this is going to give you 720 ways. Okay, notice that every one of those letters is different. Now let's take a look at the letters in the word butter. Alright, I'm going to give you a couple of arrangements here. Okay, I'm rearranging a bunch of the letters here, and then okay. In each of these two, I switched the T's. But is the arrangement different? Okay, it is not. We can switch identical objects and the new word isn't any different. Okay, so what we need to do here is we need to consider that when you're thinking about how many different ways can you rearrange those letters. Alright, and what you do is you say, alright, there are 2 T's and I can rearrange those 2 factorial ways. So to find out the number of ways something where there's repeats like that can be rearranged, you still go 6 factorial, but you're going to divide by 2 factorial, because as you can see here, we have to cut our number in half. Okay, so this is going to be 360 ways, which kind of makes sense if you think about it, that there will be exactly half as many as 720, because every time I rearrange the T's, they're the same. Okay, let's apply that to this situation. So if we took the letters in Mississippi, there are 11 letters. If I rearrange them, it should be 11 factorial. But I have to account for the ones that are happening more than once. There are 2 P's, so I'm going to go 2 factorial. There are 4 S's, which I could rearrange and that wouldn't change the word. And there are 4 I's. Okay, so maybe you want to make a comment. This is for P's, this is for S, this is for I. Alright, and that's going to give us the number of ways we can rearrange them. So let's try some examples now. In the mountainous region, India, China, Nepal, and Bhutan, it is common to see prayer flags. Each flag has a prayer written on it, and color is used to symbolize different elements. There are green flags, yellow flags, white, blue, and red. 5 different flags. How many different arrangements of the same prayer can Dorji make using 9 flags? Okay, using these types of flags. Alright, well if you just had 9 different flags, you would go 9 factorial. Okay, but some of them repeat. There are 2 white, there are 3 blue, and there are 2 red. Okay? So, I mean, that question, maybe it looked different when you read it, but really it's the same idea. And I want you to get used to recognizing that whether we rearrange letters or numbers or flags or whatever, the principles are all the same. Okay, so we can grab our calculator here to solve this one. And you would go 9 math over to probability, and then press 4. So that's going to give you 9 factorial, and we're going to divide by 2 factorial, 3 factorial, 2 factorial. And so you get that many ways. Okay, let's try the next one. How many ways can the letters of Canada be arranged? The first letter must be an N and the last letter must be a C. Okay, well, this one requires us to consider some conditions before the fact we recognize that there are 3 A's. It says we must put an N here. There's only one way to do that. And the last letter must be a C. There's only one way to do that. Okay, how many letters are left? Well, if you cross off the C and the N, there are 4 letters left. So you could put 4 factorial for the 4 letters. The problem is 3 of them are A's, so we're going to divide by 3 factorial. Okay, because if we rearrange A's, it doesn't create new words. This is going to be 4. All right, and this is a classic permutation question. You know, the first time I saw this question, I thought, well, that's a terrible question. How many different routes can take place? And I thought, well, we have to count them all. Okay, on the diagram, show the number of pathways at each intersection. So the first time I saw this, I thought, well, Bill could go this way, he could go this way, he could go this way, he could go this way, and there's so many ways, and you get lost. All right, I don't want to do it that way. Okay, I'm going to show you two shortcuts. All right, let's just consider how many ways can Bill go to this spot. He can either go like that, or he can go like that. There are two ways to get to this spot. All right, that helps us to know how to get to this spot, because there is this way, one. Okay, let me write that in a different color. There's one way, and then it's coming this way. But I already know there were two ways to go here, and if there's one way to go here, this is going to be 3. Okay, and then if I go to the next intersection, how many ways is there to get here? Well, there would be this one, and then coming this way, there are 3 ways. So if I take the 1 and the 3, there would be 4 ways to get to that spot, etc., etc. Okay, that's using the number of pathways at each intersection. Okay, let's if I continue this, all right, how many ways can I get to here? 1. That means going here would be 3. I can only get here 1 way, and that means going here would be 4 ways. Okay, and using this principle, what would it take to get to this spot? Well, I have 3 and 3, so there would be 6. Okay, what would it take to get to this spot? I have 6 and 4, so there would be 10 ways to get to that spot. Okay, and continuing this pattern, you can see that there would be 35 ways to make it there. Okay, that's one way to do it. All right, but there's another way to do it. Okay, and that is to consider how many pathways there are. Like if I want to travel in this general direction, right, I have to go up, let's call it north. I have to go north once, twice, 3 times, right? There's 1 north, there's 2 north, there's 3 north. Doesn't matter where I do it, eventually I have to go north 3 times. And I have to go east 4 times. And if you look at this as a permutation, this is 7 factorial over 3 factorial, 4 factorial. And if you do it that way, you will also get 35. I like that way better. Okay, let's try this one. The pop shop's located on a street corner as shown in the diagram. How many ways can Bill go to Jill's? But you have to stop here. So really, we're going to look at this one first. By the way, Bill can't do this. He can't backtrack. Okay? Generally speaking, you have to kind of go in this direction. Okay, how would Bill get to the pop shop? Well, he's going to travel north once and east 3 times. So this would be 4 factorial over 3 factorial. There's 4 ways to get there. You can verify that by checking the picture. Okay, and then we want to get to Jill's place from here. All right, and if we look at that, you're going to have to go north twice and east once. So this is going to be 3 factorial over 2 factorial, which is 3. So how do I get both? How do I go to the pop shop and to Jill? Well, what do we do with an and? That's multiply. So there are 12 ways. Because I have to get to the pop shop first and then to Jill's. 4 and 3, that's 4 times 3. Okay, these are all kind of the same questions. You just have to recognize that they're really asking the same thing. So this diagram says you can drop a ball and you're going to end up in A, B, C, or D, and that every time you hit one of these triangles, you have the option of going one way or the other way. So similarly to the previous one, let's kind of look at the pathways possible. There's one way to get here, and there's one way to get here. So if I keep going this way, there's again one way to get there, and then there's one way to get here. Okay, and we can do the same thing here. There's one way to get to this peak, and then to get into this partition D, there's only one way. Okay, and that would be if you drop the ball, it would head there. That's one way to get there. There's no second way to get there, because every time you hit a triangle, you end up going the other direction. Okay, so how many ways to get here? Well, that triangle could end up coming from either of those two spots, so there's two ways to get here. And then how many ways to get to B? Well, that would be 3. And that would be 3. This is actually a very famous triangle, if I write these numbers down. Can you picture what would come next? Well, you'd have a 1, you'd have a 4, you'd have a 6, you'd have a 4, and you'd have a 1. This is actually called Pascal's triangle. I don't think you need to know that, but now you do know. I'll write it down here. It's called Pascal's triangle. Okay. We don't need the second diagram. Let's go to the next example. Alright, same idea. Ryan and Patricia leave home, so that's right here, and take a taxi to the graduation party. Calculate how many different routes the taxi driver can follow to get them to their party. Alright, basically, this is 3 questions. I want to get from, let's call it, home to A, and then A to B, and then B to the graduation party. So how many ways can I get from home to dot A? Alright, I got to travel. You can go down, you could use a D for down, you can use south for south, it doesn't matter to me, but I have to go down 3 times. And then I have to go right, or east, 4 times. This is 7 factorial over 3 factorial, 4 factorial. Okay, and I need to get from A to B. A to B, there is going to be 1 south and 3 e's. That's 4 factorial over 3 factorial. Okay, and I need to get from B to the graduation party. That's going to be down twice and right 3 times. So that's 5 factorial over 2 factorial, 3 factorial. Now if I want each of those to happen, okay, this is going to be 35 and 4 and what is that? That's going to be 10. So I'm going to get 1,400 ways. All right. How many ways can the word river be found in the array of letters if you start from the top and move diagonally down? Okay, so it's given us the puzzle here. We can actually try it. I could go like this. I could go like this. I could go like that. Like that. Like that. And like that. I think those are the only ways to do it. Okay. I think that's the end of the assignment. Or sorry, the lesson. So you can go to page 266. Try numbers 1 to 13 and 15 to 18. And there is also the worksheet that is attached here. Okay, on permutations and FCP. FCP is a fundamental counting principle. All right, just some great examples on how to use sort of the lessons of the first part of this unit. Okay, so I'll also say you should do this worksheet down here. Okay, so there it is. Let me know if you have questions.